Welcome back to Asynchronous Math. My name is Mr. Frederick, and today we are going to be talking about the Pythagorean Theorem, which is a very useful equation that's as old as democracy itself. First thing we need to talk about, though, are different types of triangles, because the Pythagorean Theorem only works with right triangles. And so as you'll remember from our review in class, there are three types of main triangles: obtuse, right triangles, and acute triangles. Obtuse triangles have one angle that's greater than 90 degrees, or one angle greater than a right angle. An acute triangle has all angles less than a right angle, so there are smaller angles where the obtuse is a bigger angle, and of course a right triangle has a right angle. And because all the angles inside a triangle add up to 180 degrees, you can really only have one right angle in a triangle when we're talking about regular geometry. So if this is confusing you, come over to me, raise your hand, call me over there, and we'll talk about it some more. Or you could go to YouTube and look up right triangles. But it's very important that you understand the Pythagorean Theorem only works with right triangles. Now we can consider this blue goose. This is my friend named Georgina the blue goose. She has a lot in common with our triangles, mainly that she has two legs, and our triangles that are right triangles also have two legs. Georgina has legs A and B, just like our triangles also have legs A and B. It doesn't matter if you let A be the bigger side or the smaller side, or let B be the bigger side or the smaller side. What does matter, though, is you're consistent, because sometimes we're going to be solving for some of these missing legs, and if you name one side A and one leg B, you have to keep consistent with that. So whatever you say is the leg A is leg A, whatever's leg B is leg B. And now we know that's not the end of the story, because all triangles have three sides. So what about that third side, C? Well, this third side is called the hypotenuse. And it does matter which side you label the hypotenuse, because the hypotenuse is directly across from our right angle, denoted here in this picture by the square. So this hypotenuse is directly across from our 90-degree angle. This word can be tricky, but it's hypotenuse, not hypotegoose. No matter how much my friend Georgina would like it to be hypotegoose, it is not hypotegoose. It is hypotenuse, and Georgina is just going to have to deal with that. So now we have all three sides of our triangle. We have two legs, A and B, and our hypotenuse, C. Using these three sides, we can build our formula: A squared plus B squared equals C squared. Now what this means is we take the side A, square it, plus the side B, square it, and that's going to equal, when we add those two together, A squared plus B squared, the third side squared. And if you're still having trouble with the concept of squared and square roots, we'll be working on that in class, but make sure you check out the review of squares and square roots. Before we get into examples and the practical use of this, my friend Georgina and I would like to talk to you about the beauty of the Pythagorean Theorem. So it's geometric. You have this image, it's A, B, and C, but you have this triangle that you can hold in your hands if you were to 3D print out a triangle or to use in a graph, and it's also algebraic, meaning that we could take numbers and just plug them into the formula if we don't want to mess with a picture. In math, oftentimes we get something that's so clearly geometric or so clearly formulaic and algebraic, but this time we're very fortunate that if you like pictorial representation and you're more visual, you have the triangle, or if you're more like logical and written, you have the formula algebraically. And there's just a really cool example in math of how these two things merge together and how you need both geometry and algebra to really understand this phenomenon that's going on in the world. So now let's put this into practice. Recall that you need a right triangle in order to use the Pythagorean Theorem, and here's a poorly drawn one, but still a right triangle, with sides 3 and 3. And so we're looking for side C. So we could let, I don't know, the bottom be side A, and the right side be side B, and then we'll let the hypotenuse, which the hypotenuse is always C, I'll plug it into our formula: A squared plus B squared equals C squared. So now we take values 3 for A and 3 for B and plug that into our formula, so we get 3 squared plus 3 squared is still equal to C squared, and what that really means is we have 3 times 3 plus another 3 times 3 equals C times C. So then 3 times 3 is 9, another 3 times 3 is 9, so 9 plus 9 equals C squared. 9 plus 9 is 18, and that equals C squared. Now remembering our square root rules, and if you're having some trouble with square roots, we're going to have a tutorial on that, or see some more stuff in Canvas. We're going to take the square root of both sides, and we see that C is equal to the square root of 18, and that's a fine answer for right now to leave that in. The square root of 18, that's an irrational number, And so it's not going to have a pretty decimal, and so we can leave it. But we could break down 18 into 2 times 9, and the square root of 9 is 3, so we're able to pull out a 3 into the front. So c could equal 3 times the square root of 2, but the c equals the square root of 18 is fine for our purposes today. Now we're going to move into a second example where we have one leg equal to 3 and the hypotenuse equal to 5. And we're trying to find the missing side. So we could name either leg either things. Let's go 3 is equal to A and our missing side is equal to B. And then of course 5 is across from our right angle, that's our hypotenuse, and 5 will also be the length of side C. Recalling our formula, a squared plus b squared equals c squared, we can take our value for a, 3, and plug it in for a, take our value for c, 5, and plug it into c in the formula. And so we get 3 squared plus b squared equals 5 squared. And of course that's 3 times 3 plus b times b equals 5 times 5. So it's a bit different than our formula last time because now we're solving for a missing side. So we get 3 times 3 is 9 plus b squared equals 5 times 5, 25. Now it's just an equation from there, subtract 9 from both sides, and b squared is equal to 16. Now we take our square root, and b is going to be equal to positive or negative 4, because whenever you take a square root you get a positive or negative, but we're talking about distance, that wouldn't make sense, so we just have positive, and so we're going to have b equal to positive 4. And that's going to check out, because if we look at our image now, we can see on the units, b is actually 1, 2, 3, 4 unit squares long. And you may have noticed this relationship before because it's a Pythagorean triple. So one of our triples is 3, 4, 5. And so this is when we get whole numbers out of our Pythagorean theorem. That's what makes the Pythagorean triples so special. So we've seen this in a few of our class examples, but if you put in 3 and 4 for A and B, you'll get 5 out for C. 3 squared is 9, 4 squared is 16, 9 plus 16 equals 25, and 5 times 5 is 25. So that triple does in fact check out. The next smallest triple is 5, 12, 13, so 5 squared plus 12 squared is going to equal 13 squared, 5 squared is 25, 12 squared is 114, and then 13 squared is 169, and that relationship also holds. But it doesn't have to be whole numbers. This relationship between the square of the leg and the square of the other leg and the square and the hypotenuse holds even if we had crazy decimals, even with irrational decimals. And that's pretty wonderful when you think about it. And you'll get a chance to play and kind of explore this in our Desmos activity this week. But as you can see on my screen, that as I move these lengths and make these squares bigger, that in turn makes the hypotenuse square bigger. And they always, always, always equal each other, the squares on a right triangle.